Hello and welcome to my presentation on explorable uncertainty in scheduling with non-uniform testing times. My name is Alexander Eckel and this is joint work with Susanne Albers. In this talk, we consider a scheduling problem on a single machine with testing. We are given a set of jobs whose processing times pj are unknown. They are upper bounded by some numbers uj, and there is also a testing time tj for every job. An algorithm wanting to solve this problem can now either run the test tj to reveal a job processing time pj, or run the job j untested, which takes time uj. Let us consider this 4-job example that we have here. The first job has a rather short testing time t1 when compared to its upper bound u1. So we might want to test it. Running its test reveals the processing time p1, which you can then schedule. The second job has a rather large testing time when compared to its upper bound. So we might want to decide not to test it. We can schedule the upper bound u2 on the machine. Of the two remaining jobs, 3 and 4, the fourth one has the smaller testing time. So we decide to test that one first. It is revealed that the fourth processing time, p4, is rather large. It's almost the same as the upper bound. So we decide not to run it immediately, but instead first test the third job. This reveals that p3 is actually rather short. So we first schedule p3 and then p4. After this introductory example, let me define the problem formally. As we have seen, we are given n jobs with unknown processing times pj, which are upper bounded by uj. We have also the testing times tj. An algorithm who wants now to solve this problem has now two possibilities: either to test and then later execute a job, which takes a total time of tj plus pj, or to execute the job untested, which takes time uj. Let now cj be the completion time of a job j. We consider two objectives. First, the makespan, which is just the maximum completion time of any job j. And second, the sum of the completion times. Later, we will also differentiate between deterministic and randomized algorithms, as well as the preemptive and the non-preemptive setting. Let us first consider an optimal algorithm, which has full information about all the parameters of the problem. In particular, it also knows the processing times pj of any job. Since this optimal algorithm knows the processing times, it will test a job j only if tj plus pj is actually smaller than the upper bound of the job. This then gives us an optimal offline runtime of a job, which is just rho j, the minimum of these two numbers. With this, we can compute the optimal offline values for our two objectives. For the makespan, this is just the sum over all the rho j's, giving us the optimum. For the sum of completion times, we need to assume without loss of generality that the rho j's are ordered by non-increasing size. So that means that rho 1 is the largest optimal offline runtime and rho n is the smallest. Then, since the optimum orders all the jobs by the optimal offline runtimes, rho j, we can write the optimum as the sum over all j's of j times rho j, because the largest job is at the end and is only counted once. The second largest job is before that and is counted twice, and so on and so forth, while the smallest job, rho n, is counted n times, giving us this formula. Knowing these values of an all-knowing offline algorithm, we now consider an actual algorithm that does not know the processing times pj. We may consider such an algorithm to be online, since the job processing times are revealed one by one whenever a test is completed. We can then also consider the competitive ratio, which is then just the worst case ratio between the value produced by the algorithm and an optimal offline solution, leading us to the definition of the standard competitive analysis. In order to be competitive, an algorithm has two main decisions it has to face during its runtime. First is whether or not to test a job or to run it untested. This is usually decided on a per job basis. In most of our algorithms, this is decided collectively for all jobs in the beginning of the algorithm, but we might also do that during its runtime. The second decision concerns the order of the job executions. This is of course not relevant for Makespan minimization, but is very important for the sum of completion times. Since we do not have full information about our input, it is hard to sort, as usually in sum of completion times, by increasing order of execution size. We have two types of executions that we want to consider in our case: the tests and the already known executions, which could be either an upper bound or a revealed processing time. Of those two, we want to prioritize the known executions, since tests only lead to some new information being revealed, and the known executions actually lead to a job being completed, which of course we want to prefer. We have tried to reflect this idea of lowering the relevance of testing in our main algorithm. Before we present our results, let us briefly talk about some related literature. Research on querying uncertain parts of the input has been around since 1991, when Kahan published his initiating work on the topic. In his paper, he is concerned with minimizing the number of queries to determine certain function values. Since then, there has been extensive work on the topic. Please consult our paper for an overview over important publications. On the other hand, there are settings where the cost of the queries is a direct part of the objective function. These include, for example, Weizmann's original Pandora's box problem or the so-called price of information model, as introduced by Singler in 2018. This is also where our setting of scheduling with testing fits into. It was introduced in this form by Dürr et al. In 2018. As we have seen, query costs there are paid on the same machine as the scheduling costs, so it fits into this setting where the cost is part of the objective function. Dürr et al. Only considered the case where the tests are uniformly equal to 1, and they presented results for deterministic and randomized makespan, as well as the sum of completion time. We present these results on the next slide together with our results for the general case. We have considered the deterministic and randomized settings, both for the objective of minimizing the sum of completion times, as well as the objective of minimizing the makespan. Our results for these can be found in the general tests column. The results of Dürr et al. Can be found in the final two columns. We have also additionally considered the deterministic preemptive setting for the sum of completion times. Since there has been no consideration of this objective in Dürr et al., we have additionally constructed a lower bound for this case. In this talk, I want to focus on the deterministic setting. Let us first start with the Makespan minimization. As mentioned before, the job order does not matter for this objective. As we can see in this example here, both schedules have the same makespan, even though the ordering is different. This of course means that worst case instances may consist of a single job only, and that we can decide testing on a per job basis. An optimal algorithm by Dürr et al. 2018 has been presented for uniform testing. This algorithm can be easily extended to the general case, as we will show in the following. In order to understand how this optimal algorithm works, consider these two example jobs. Recall that worst case instances consist of only one job for the Makespan minimization. On the left we have the job J, whose testing time Tj is very small compared to its upper bound Uj. That means that the ratio Rj between the two is large. This might lead us to the conclusion that it is prudent to test the job. If we do that, the processing time Pj is revealed, which we can then schedule on the machine as well. Now, if the optimum was actually also testing the job J, then this is optimal. But on the other hand, we have a problem, because that leads to a bad case. The algorithmic time, so the time that the algorithm needs to schedule the job, is Tj plus Pj. But now we can estimate that against Uj divided by Rj, because that is the definition of Rj, plus Uj, because Pj is always upper bounded by Uj. This gives us the optimum times a factor of 1 over Rj plus 1. On the other hand, consider the second job, K. Its testing time Tk is very large compared to its upper bound Uk. It's almost the same. So that means that the ratio Rk is now small. This leads us to the conclusion that it might be wise to run K untested. If we do that, and the optimum has done the same, then again, this is a good case, and the algorithmic time is the same as the optimum. But on the other hand, in the bad case that the optimum is equal to Tk plus Pk, so the optimum tested the job, we can estimate Uk, so our algorithmic time, by Tk times Rk, by the definition of Rk, which is then smaller than the optimum times rk, since the optimum is tk plus pk, so at least as large as tk itself. As we can see, in both cases, we have a factor times the optimum in the bad case. If we want to now minimize these two factors, we want to minimize the maximum of the two. So we want to minimize the maximum of 1 over r plus 1 and r. It can be easily seen that this is minimized exactly at the golden ratio. Therefore, we construct an optimal algorithm by testing a job j if and only if the ratio of the upper bound and the testing time is larger or equal than phi, where phi is just the golden ratio. The algorithm with this testing condition is then exactly phi competitive. Also, no deterministic algorithm can achieve a smaller competitive ratio. Additionally, we also constructed the corresponding randomized algorithm, which tests the job j with a certain probability and is 4 over 3 competitive. Again, no randomized algorithm can achieve a smaller competitive ratio, as has been proven by Tur et al. Having solved the objective of minimizing the makespan optimally, we now consider the sum of completion times. For this, we have devised the following algorithm framework, which we call alpha-beta sort. Similarly to before, for every job, we decide the testing based on whether the ratio between the upper bound and the testing time is at least as large as some parameter alpha. Then, and this is different from before, we have to sort the jobs. We do this by considering the so-called scaling time, sigma j. If a job j is run untested in the algorithm or has already been tested by the algorithm, then the scaling time is just the time necessary to schedule the next step of the job. But on the other hand, if j is planned for testing but has not been tested so far, then the scaling time is actually equal to beta times tj, where beta is the second parameter. So we have two parameters in our algorithm that correspond to the two main decisions the algorithm has to make in our problem. The testing parameter alpha decides whether or not a job is tested. The sorting parameter beta artificially lowers the relevance of testing in the ordering of the algorithm. To receive the best possible result, we ran a parameter optimization over these two parameters, and as a result, received that setting both to 1 is the best possible. Therefore, it has turned out that the 1-1 sort algorithm is 4 competitive for the objective of minimizing the sum of completion times. Let's briefly sketch the proof of this result. The main tool that we use for this proof is the so-called contribution of pairs of jobs. We define C of k and j to be the contribution of a job k to the completion time of the job j, which is just the amount of time that the algorithm spends scheduling anything related to k before j is completed. If we look at this short example here, where we want to compute C42, which is the contribution of job 4 to the completion of job 2, we see that it is everything the algorithm schedules before 2 is finished. Since 2 is only finished at the end of this example schedule here, we have that both the testing time and the processing time of job 4 is included in the contribution C of 42. This means C of 42 is equal to T4 plus P4. Using these definitions, we can then prove the so-called contribution lemma, which is a central lemma in our paper. The first part of the lemma tells us that the completion time of a job j can be computed by summing over all the contributions of jobs k to j. The second part then upper bounds a single contribution c of kj by a constant in alpha and beta times the optimal offline running time rho j. We prove the contribution lemma by going over various case distinctions concerning the jobs k and j and their testing status. We now want to upper bound the completion time of a fixed job j. We can do this by considering all the contributions of other jobs k to j. For this, we may make a case distinction into two cases. In the first case on the left, we consider a job k whose index is larger than that of j. Recall that the jobs with large index were exactly the jobs whose optimal offline running time, rho k, is small. So in this case, we may estimate the contribution of k to j by directly taking the maximum running time that a job k can have in the algorithm, which is just the maximum of tk plus pk and uk, which you can then simply upper bound by another constant in alpha and beta times the optimal offline running time rho k. In the second case, where the index of k is smaller than that of j, we just use the contribution lemma, which is independent of k, and therefore avoids the potentially large contribution by the optimal offline running time rho k. Combining these arguments, we can then compute the value of the algorithm, which is just the pairwise combination of all contributions of jobs k and j. This we can then upper bound by another constant in alpha and beta times the value of the optimum. Afterwards, we then do an optimal parameter selection for the two parameters alpha and beta, which leads to values alpha and beta equal to 1. We have chosen alpha and beta such that the closed upper bound formula that we've just received in our proof is minimized. Of course, this might not have been the best choice for these parameters. For 1, setting alpha to 1 means that we test all non-trivial jobs. Similarly, setting beta to 1 means that we do not prioritize executions over tests. It is likely that the upper bound we received is not the best possible. In practice, it might actually be better to set the values of alpha and beta to something a bit higher. For example, setting a higher alpha value means that we get better bounds for single jobs, as we've seen in the Makespan optimization. Setting beta to some higher value lowers the relevance of testing, which was the intuition that we had in the beginning. As can be seen in some of the algorithms for the uniform case, or some of the algorithms that we will present later, setting alpha and beta to some higher value makes sense, but for the closed formula that we received in our proof, alpha and beta equal to 1 is the best choice. In order to better judge the performance of our 4 competitive algorithm, we have also proven some algorithmic lower bounds. Because of the somewhat unexpected choice of parameters for the 1-1 sort algorithm, we are able to prove that it is not better than 3 competitive. Additionally, we have also proven that alpha-beta sort for any choice of parameters alpha or beta larger or equal than 1 is not better than 2 competitive. Before we conclude this talk, let me briefly mention 2 other algorithms that we considered in our paper. First is the randomized setting. Based on the deterministic algorithm alpha-beta sort, we have constructed the so-called algorithm randomized sort, which takes the testing parameter alpha and makes it randomized, such that we test with a certain probability given by P of Rj. This means it still depends on the ratio between the upper bound and the testing time. The sorting parameter beta is not made random. Instead, we determine the optimal deterministic value based on the probability function P of Rj. The resulting algorithm randomized sort is then 3.3794 competitive. Let us take a short look on how the parameters p and beta are chosen in the final version of the algorithm. The probability function is chosen according to the function p hat that we can see here. The blue line is the value of p hat for the ratio r between the upper bound and the testing time of the corresponding job. As we can see, between 0 and 1, this value is 0, which makes a lot of sense because if the ratio is less than 1, that means the testing time is larger than the upper bound, and that means we shouldn't test. From 1 to about 1.3, the probability then linear increases. From 1.3 to 2.2, it then tapers off until for values higher than 2.2, we just set the probability to 1. So that means between 1 and 2.2, we slowly increase the probability of testing the job, and then for higher values, we just always test the job. If we combine this definition of p hat with the final definition of beta hat, which is about 1.26, then we can get our final competitive ratio for the algorithm, which is 3.3794. Additionally to the randomized setting, we also considered the preemptive deterministic setting. In the preemptive setting, we are allowed to interrupt the processing of a job at any time in the schedule and replace it by a different job which is then scheduled. For this setting, we constructed the golden round-robin algorithm. As before, we decide for every job in the beginning of the algorithm whether we test it or not based on whether the ratio between the upper bound and the testing time is larger or equal than phi, where phi is again the golden ratio. Then in the second step, we run all jobs in a so-called round-robin scheme. Round-robin is a rule which is frequently used in preemptive machine scheduling. And it works as follows. We first divide the scheduling time frame into very small equal-sized units. The algorithm then continually cycles through all these jobs, tending to each job for exactly 1 unit of time. This leads us to a schedule where at any time the amount 2 jobs have been processed differs by at most 1 time unit. In our paper, we proved that the golden round-robin algorithm is 2-phi competitive, which is about 3.2361. In the proof, we use again cross-examinations of contributions of jobs, and then use the special structure of round-robin to further improve the result. I have already talked about the algorithmic lower bounds for the 1-1 sort and alpha-beta sort algorithm. In our paper, we additionally prove an algorithmic lower bound for the golden round-robin algorithm, and that it is not better than 2-phi competitive. Since we have also proven that it is actually 2-phi competitive, this means that the analysis of golden round-robin is tight. The paper by Dürr et al. Did not consider the deterministic preemptive setting. Therefore, we used their lower bound for the deterministic non-preemptive setting and adapted it to the preemptive setting, proving this general lower bound, in that no algorithm in the preemptive deterministic setting is better than 1.8546 competitive. With this, we have covered all results in our paper. Here is again the overview of all results in scheduling with testing, both for the general and the uniform test case. Apart from tightening the gaps between the results, there are some other possible directions for future research. So far, almost all algorithms and lower bounds that have been considered make decisions based on fixed rules that do not change during the runtime of the schedule. We might improve algorithms and adversaries by letting them decide things like testing and the order of jobs dynamically. Analyzing such dynamic decisions is hard, so we could, for example, start by dividing the schedule into a fixed number of time frames, each of which is then handled separately. Another interesting topic could be dedicated lower bounds for general tests, since all lower bounds so far also hold for the uniform case, and we might be able to improve the bounds by considering general tests only. Finally, the problem can be extended to multiple machines or other popular scheduling settings, like OpenSharp, FlowSharps, or parallel machine settings. With this, I want to conclude the presentation. I hope you enjoyed my talk, and thank you very much for listening.